I'm here with Martin Schreyer, who is an application specialist at Malvern Panalytical. Welcome, Martin. How are you today?
Oh, today I'm fine, thank you.
Good. You've been in this field of expertise for quite some time. How long have you been in the field?
Well, actually, I started collecting my first patterns in 1995 during my diploma thesis. And I never expected to go into that field.
Why not?
Well, I'm an inorganic chemist, so my dream was making high-temperature superconductors and without copper, please. And obviously, I didn't manage.
But you found a different passion.
Yeah, I found a different passion, so I got more and more into this. So suddenly I ended up teaching powder diffraction, and then, yeah, now I'm working for a manufacturer of powder diffraction equipment, and I can't say I regret it, quite on the contrary.
Okay, well, that's good to hear. We just talked about powder X-ray diffraction. Today we're going to talk about scattering techniques, and apparently humps have information. Explain.
Exactly. Well, basically, when I started up in 1995, the expectation was low background, good peaks, and then you have a good sample. And if you had then something that had a pattern like you had a bad sample, please come back when you got a good one.
Oh, so you expected something flat or...
Yeah. So it was literally a technique reserved for, well, just very nice and crystalline materials and good samples, and all the rest was discarded. And you have two regions of interest, actually. So one is very, very close to the origin, so at around 0 degrees to perhaps, let's say, 5 degrees.
Yeah.
And that contains information about larger objects. So things like micelles, for examples, or proteins and nanomaterials. You can get some information about particle size, particle shape from that region.
So the humps actually have relevant information, that's what you're saying, instead of what we used to think, it doesn't matter.
Exactly.
Okay.
And so this low angle range, where you have often just a little bit of a slope, that has some relevant information about larger objects. When if you go to the other side, where you have those humps, you have also information, and those are informations about the local structure. And it has turned out that you can probe that best if you use very hard, that part best when you use very hard radiation, like molybdenum or silver, if you have a laboratory source, of course. And and you collect as far out in angle range as possible. And then the high angle part here, which is seemingly featureless, actually contains the fingerprint of the molecules. So it could be, I introduced a tablet that last time, which was working faster than the other. I've got one here.
So that's an ibuprofen pill.
Yeah. It could be that this doesn't really give a good powder pattern, but that actually it is amorphous. And then, if you want to characterize it, how that is organized, at least on a local scale, then you would go to collect a powder pattern with, let's say, molybdenum radiation or silver radiation up to 120 degrees or even further. 140 degrees, I think, is what we can do. And then you would process the data, so you would fill this into a capillary, and then you would measure that capillary. Then you would measure an empty capillary the same way, when you would subtract the empty capillary, and then you would post-process the data.
Okay.
And post-processing contains several steps. So you would subtract the empty capillary. Then you would do some kinds of normalizations. So putting the intensity on some kind of absolute scale. So normally the intensity depends also on the intensity of your X-ray source. And then you would do something that is called a Fourier transformation. Fourier transformation, you don't really need to know too much of it, but it's what is, for example, used when you are converting a soundtrack into an MP3 file. It makes it much more compact, and
you're compressing
data. And here you are also changing the length scale. So you're just going from angles, what we had before, or Q vectors as we call it, to actual distances. So, and then you get a pattern that looks a little bit like this. So tails out at high distances, and that gives you a radial distribution of next door neighbor. So imagine you have a square lattice of atoms, and when you go a certain distance and when you probe, so how many atoms do I find in that distance? Maybe 4, maybe 6. Depends on the kind of lattice you're going. When you go further, when you have your next round, and so each of these gives a peak in, and that is what we call a pair distribution function, and that gives me information about the molecular fingerprint. Is the molecule in a boat shape, or is it in a chair shape? That would be the other possibility that exists. And you could also see, is my amorphous truly amorphous, or is it actually a nanoparticle?
And why would that matter?
Well, if it's not truly amorphous, it may be a patented, may be related to a patented crystal structure, which you may want to avoid.
Yeah.
Or it could tell you about how to optimize the process to get to that particular amorphous. So amorphous is not necessarily equal amorphous. So what I've learned when I was working somewhere else was that if it depends on the drying process, which kind, or original solvent in that case, which kind of amorphous you get.
Okay.
And so there are different amorphous phases as there are different crystalline phases. And you can distinguish them with this technique. So that's the PDF technique.
And what's the other technique? So there's the PDF technique and there's a second one, I think.
Yeah, small angle X-ray scattering. So small angle X-ray scattering, as I introduced a little bit earlier, is about the low angle part. Here, the softer the X-rays, the better. Typically, most people use copper radiation, but cobalt radiation is even a tad better. And in that case, you go through similar steps of data acquisition, and also similar steps of measuring the sample. So you would fill it in a capillary, for example. And then you also do the Fourier transformation often. And that gives you something that they call pair distance distribution function. So you're no longer looking at atomic distances, but at the size and shapes of particles.
Yeah.
And for a protein, it would tell you what is the shape of a protein. Give you a first idea, and then you could start modeling the structure with mathematical models. And or if you're having COVID vaccines, they're typically embedded in lipid nanoparticles.
Yep.
So it would tell you, okay, how thick are the layers on the outside? How is the contrast of the inside? What is the difference between a loaded nanoparticle or an unloaded nanoparticle?
So when would you choose PDF over the other option?
When I'm interested in on the large scale, when I'm using small angle X-ray scattering.
Yeah.
And so for biomolecules, or if I wanted to probe emulsions, lipid nanoparticles and the like, when I would go for small angle X-ray scattering. If I'm interested in small molecular structure, then I'm more interested in the PDF technique.
Okay. Anything else we need to know?
Well, both of these techniques, as well as powder diffraction, can be done on a modern powder diffractometer, a multi-purpose powder diffractometer like you're seeing here, the Empyrean. And if I wanted to reset the instrument from one technique to the other, it takes me about 40 minutes, because I also need to change the radiation tube, but to get from one setup to the other, and I'm ready. It's very easy to do.
Yeah.
Yeah.
Very easy to do. Okay. Well, thank you for this introduction.
You're welcome.